Okay, so this is on again, I think. Yes, I can hear myself even. Very good. So I'll continue from where I left off. So I got you all the way to this, what I call the second paradigm of quantum chaos, which is also known under the name of the eigenstate normalization hypothesis. And it's a statement about the matrix elements of some, let's call it local operator in the basis of the Hamiltonian, and it contains in particular two smooth functions, A over line of E and F over line of E and omega. And it contains this entropic suppression where S of E is the microcanonical entropy of the system at average energy E. And it contains the fluctuation contribution, which is here denoted by Rij, which is actually a random matrix. It's a Hermitian random matrix. And in some sense, I have absorbed its mean and its variance in this function f. So we can now say that this is a function that has mean 0 and variance 1 by normalization. And so now, so in the, well, often one reads that this should be a Gaussian random matrix, but in fact, in recent years, we've learned that it should be non-Gaussian, and I will just make one remark about this. So in particular, what I just said, that it's just specified by its mean and its variance is not correct. And so the non-Gaussian statistics, so let's say the connected higher moments, also known as non-Gaussianities of Rij, in recent years have been important in the following, actually, several areas. So one is that it was realized that, for example, if you want to understand the physics of scrambling, as we will do in a few moments, or maybe tomorrow, I'm not quite sure, physics of scrambling, then you need to understand the non-Gaussianities of this Rij. So scrambling is also some measure of it's also a measure of quantum chaos. And it has been very important and very instrumental in something that we developed in the context of gravity, which we call the DTH matrix model, which actually is a matrix model type description of what's called JT gravity coupled to matter. And also in what is essentially the extrapolation of this ETH matrix model to higher dimensions, which is, BDJNS tensor model, which again are two topics that, well, certainly this one I hope to have some time to talk about in the last lecture. But so anyway, so that is something, it's just a sort of like previewing something I might get to later on. But, yes?
But is there like in any many-body scenario that you see that you need a non-Gaussian?
Well, just for example, in any many-body system that has a non-trivial scrambling exponent. So yes, in fact, I would say, as far as my understanding is concerned, in all of them. Of course, these non-Gaussianities are as such very highly suppressed. They are suppressed. There are some non-Gaussianities, we would call them, I don't know, Gn. And so this f here will be something like G2, and the Gn would be like e to the minus n minus 1 s over 2 suppressed in some sense. So as far as the matrix elements are concerned, these are extremely small corrections, but in fact they can have order 1 manifestations in relevant physical quantities. Okay, so, now, for now, we just take this statement here for, it's actually a statement about both the one-point function of the operator and, if you want, even its fluctuation, namely the two-point function, which is encoded in this f function. And so the point of this ETH ansatz, which I believe historically was motivated also from studying the matrix elements of semi-classical chaotic systems, but is now understood to be not necessarily tied to that. But so this form of the matrix elements essentially ensures thermalization in the following sense. So from this we get, again, quantum thermalization. And I call it quantum thermalization because you already notice that in some sense it takes a very different flavor than what we talked about in classical thermalization. For example, if I look at the expectation value as a function of time of some operator A with respect to some superposition of eigenstates around some energy E. Okay, so now I have some pure state, but it is a superposition of many of these eigenstates. Then, of course, a simple calculation will show you that you get something like the coefficients in this expansion, C alpha squared times the diagonal contribution, plus you get the off-diagonal contribution alpha different beta of C alpha C star. I mean, I'm just doing like very simple quantum mechanics here, times A alpha beta off diagonal times E alpha minus E beta, yes, times T. And well, sorry. I say I'm doing very simple quantum mechanics, but I'm actually not able to do it. Yeah, A alpha alpha. So I'm just doing the time evolution of this quantity with respect to some psi, which again I want to be like a state that has, let's say, in the thermodynamic limit, finite energy density. And now the idea is that, well, we have no degeneracies here. That's something that we learned from actually earlier, because we said that in a quantum chaotic system, the levels don't like to be near each other. We had this distribution of levels went to 0 at the origin, so there are no degeneracies, and at least once you mod out by symmetries. And so actually what happens is that this will become at late times a wildly oscillating function, and will average to 0 by any time average you do. So you end up not seeing the off-diagonal elements. You project on the diagonal elements, and you basically, on the diagonal elements now, recover this A of E delta ij, which often is said to be the microcanonical average, but it's not strictly necessary to say that. So we then find, in other words, that something like A of t, but let's say now averaged, which is something like the limit, so 1 over t of A of t as a matrix value, d matrix as an expectation value, 0 to t. So I average over a time interval, and I can formally extend that time interval to infinity, that on average, this thing will actually converge to precisely this diagonal ensemble, which is something like C alpha squared times A of E. And then the statement is that in a sufficiently small, let's say, microcanonical window, this function, because it's a smooth function, it will basically not change. It will be almost constant. In particular, will not depend on this discrete summation index alpha. So I can take it out. I can do the sum. And of course, this is just a normalization constraint. So in other words, this thermalizes to A of E. And so the process of thermalization of observables in a chaotic quantum system is actually a process of dephasing. The thermalization here is actually a result of the dephasing of the off-diagonals, and together with the fact that on the hypothesis of this ansatz here, what hides on the remaining diagonal is a smooth function of energy, and in most circumstances it will be identified with the microcanonical average itself of the expectation value. So in some sense, what the eigenstate thermalization hypothesis says is pretty wild. It says that actually at the level of individual eigenstates, we already have thermal information, which is normally information about a wide range of the spectrum of the system. And here it is in this A of E along the diagonal delta ij. Now, of course, okay, so in that sense, this ETH ansatz is great because ETH essentially tells us that you get thermalization of non-extensive. Earlier I called them local, but sometimes I prefer calling them non-extensive quantities. And then, of course, I also have to add this on average, because in order to see the thermal character come out, I do need to do some averaging, for example, here time averaging. And now, however, again, you can actually go further because the fluctuations, for example, fluctuations, just the simplest, let's say, variance of this observable, the fluctuations are encoded. So here in this e to the minus s over 2 f of e omega rij bit, and in particular can be shown to obey standard thermal notions such as fluctuation dissipation relations. So that's nice, and so that is giving you a sort of replaces this classical development, time development of phase space distributions under chaotic and mixing dynamics to get a thermal state with some notions that are intrinsically natural in quantum systems. And nevertheless, you get the sort of basic tenets of statistical physics, such as fluctuation dissipation relations and so on from it. Very good. So now, in other words, so if I understand or if I remember correctly, the historical development of this is that these ideas were around for quite a while, but maybe at first look they do appear a bit implausible if someone looks at a quantum system and says that statistically speaking I can replace the matrix elements of some operator A with something that looks super generic, and in fact thermal information is already in the matrix elements of individual operators. But at some point people started testing this in particular numerically, because you see, of course, one of the big challenges in this kind of subject is that these are statements about generic chaotic systems which are very difficult to solve. It's very difficult to actually come by models of chaotic dynamics that are actually also solvable. I mean, that's more the domain of integrable systems. So actually numerical investigation of the validity of this ETH ansatz really has played a crucial role in people accepting that at least there exists a large class of systems where this is really true, and where this is really the mechanism, if you wish, of thermalization. All right, so we've now seen two intrinsically quantum ways of thinking about chaos. One was the spectral chaos, related to the eigenvalues and the eigenfunctions, random matrix theory, where we could say that for the purpose of understanding, for example, eigenvalue gaps on average over the spectrum, we could replace the physical Hamiltonian of a system with a matrix integral. And we've seen that the operator matrix elements can be understood in some sense in a similar way by replacing, in a statistical sense, the matrix elements by something that is deterministic but also has this random matrix contribution Rij. In fact, by the way, that the fact that you have these two random matrix occurrences of random matrices in both of these paradigms, at least to us, was very suggestive. And this is why we wrote down recently this thing that we called ETH matrix model, which actually both describes the paradigm 1 and paradigm 2 in one sort of unified framework. And if you're interested in that, you can either ask me or you can look at the paper that we wrote on this of that title. This was with David Kolchmeyer, Dan Jaffress and Bar, Mohamed Sanof. Anyway, so however, I wanted to say one last thing about quantum chaos, and this is the one that in some senses maybe the least quantum, but it's the one that will make contact with something that we've seen before, and that's this idea of a quantum Lyapunov exponent. And this goes back actually to the late 60s to Larkin and Ovchinnikov, who were studying essentially disordered superconductors at the Landau Institute, but lay dormant for a while and has only in the recent decade again come to prominence. And so one way of getting there is actually an information theoretic way of thinking about that, which I will get to on a second round. But the way to kind of motivate it from what we've seen before is that we have said, roughly speaking, we should associate this exponential divergence of trajectories with this Poisson bracket on phase space. And of course, if we follow Dirac, then associated with this is actually a semi-classical notion of a quantum observable, namely, I promote now Q to an operator, let's say a Heisenberg operator, and P also to an operator, and I look at the semi-classical commutator. Semi-classically, we have the correspondence between Poisson brackets and operators. So that's, I think, also what Larkin and Ovchinnikov said, and they were interested in extracting something like a Lyapunov exponent from this quantity. And what they basically showed, so let's say this suggests, so is this something like quantum Lyapunov? And what it means is that you look at the time evolution of the Heisenberg operator P of t, and you see whether it develops some interesting dynamics in the commutator with P. But of course, it's quantum mechanics. So we need to ask also, how do we evaluate this? And what has been suggested, or what has been used, is that actually you look at the thermal expectation value of this guy. And for reasons that are always a bit mysterious, you want to look at the square of this commutator. So somehow a reason that is often given is that if you just were to look at the commutator itself, there are phases, and you find that they will dephase, and you actually find that this usually vanishes. So you have to look at something which is more like an absolute value. So you look at the square, and this is the quantity that you want to look at. And I actually want to look at this with respect to a thermal density matrix. So actually what I want to look at is trace e to the minus beta h of q of t p all squared. Now, what you notice, of course, is that that's something like q t p0 q t v0 plus P0 Q at t, P0 Q at t, plus two more terms that we will call time ordered. And the reason being that the ones that I wrote are out of time order. Because what you do is that if we read it now again as Schrödinger picture, we go from 0 to t, back to 0, back to t. So these operators are out of time order. And they're not, as such, a physical quantity that you can simply measure. Because if you wanted to set this up as a measurement, then you would have to be able to turn back time at intermediate results of the procedure. There exist protocols, by the way, which allow you to, in principle, measure such things. And that's an interesting subject in itself. But they typically also involve going to circumstances where you have more control than, let's say, just what, let's say, a physicist would do and hooks up a piece of matter and measures resistances and so on. So it is typically done in highly controlled quantum devices. This is not like a very natural physical observable. But for now, as a theoretical quantity, it turns out to be very interesting. So I will actually argue that in a second. The interesting Lyapunov behavior is in the out of time order correlation function. I don't know if I can motivate very quickly why that is, but one way, if you have some familiarity with this, is that it's closely related to something that people will call a Low-Schmidt echo, where you have a chaotic system and you evolve it forward, and then you evolve it backwards in time with a Hamiltonian that is slightly perturbed. And of course, because there's a slight perturbation between going forward and backward in a chaotic system, you expect that there are large, even exponentially strong divergences between going forward and backward in time. Whereas, if you had u times u dagger, you would get 1. There would be nothing interesting. If you have u times u dagger prime, you can get something that has this flavor of the butterfly effect. And so this repeated forward, backward, encodes essentially the same idea. Okay? That's also why people like to call this the quantum butterfly effect. But there is actually, I think, a more intuitive way of saying the same thing. But for this, we can even go and say we can look at more general out of time order correlators. So there is no reason actually to restrict ourselves to just momentum and position operators. That came from sort of a classical notion. And so in one just defines the following quantity. One says, let's say we have a function that depends on time and in principle could also depend on position. R could be some radial separation between these, let's say if the system is isotropic for simplicity. And I say that I actually take the expectation value of some operator, W dagger, at t at the origin, V at time is equal to 0 and at some point R, W of t 0, V of 0 R with respect to some state, but again, most of the time people put here the thermal density matrix. Although there's some subtlety which you will also learn about in a second. And the statement is that this also governs the late time behavior of what? Well, of a function that is closely related to what we started with, C of t and R, which is the thermal expectation of WT V R dagger WT V R in the thermal state. So it also measures the commutator as a function of time of it's in some sense the norm of the commutator. Norm of the commutator of these two operators. And now we're sort of in business. So first of all, we can write the following. Okay, we can write that this is equal to f of t r plus f star of tr plus time ordered. And then the time-ordered ones actually simply by cluster decomposition will factorize and will become products of two-point functions and therefore decay at a time which I will call time beta, local thermalization scale time, which is basically given by the temperature, or people also sometimes call this dissipation time. As I said, I prefer actually local thermalization time, but at any rate. And the late time behavior will then, so if you go beyond this dissipation time, will purely be governed by these out-of-time order correlators. They sort of give you really the essence of the behavior of this commutator. And it's an information theoretic picture here is the following, is that you have, let's say, the arrow of time in this direction, and we take some snapshot where, say maybe at the beginning of our experiment, and what we have is we have the situation where there is some operator VR, and here's our operator W0 at time t is equal to 0. Time t is equal to 0. And then as time actually progresses, what happens is, so this is supposed to be some, let's say, spatial view of our system, and I'm looking at some subregion, perhaps could also be the whole system, but let's say the subregion, where W is located at position R, and W0 is at the origin, and I'm taking the snapshot as time is equal to 0. If I look at some intermediate time, let's just say the intermediate time, what will happen is that actually if you wish, the influence, the Heisenberg evolution of the operator W starts having the effect that the degrees of freedom that are influenced by, let's say, what used to be a local perturbation at the origin extends now over a larger region of the spatial part. So this is like W at t intermediate, and I have V of R here, until eventually at some t is equal to t scrambling, I have that V is actually squarely in the region that can be influenced by the spread of this perturbation. And therefore, at the beginning, we have that W0 and V are actually commute. Okay. This is, if you want, also part of the setup. I'm supposed, for this to be an interesting quantity, I'm supposed to choose two operators that at time 0 commute. Now here, even though maybe the picture doesn't say that, maybe there's some sort of low density of this that's already leaking here, it's a little bit blue. Okay. What I'm trying to say is that at this point, W0 VR, and let me just put a norm here, actually starts growing. Okay. Because if I didn't put the norm here, I would myself not be sure if I would say it increases or decreases. Depends on how you define your signs in the beginning. I wasn't careful about that. And here now, around the scrambling time, this should already be WT, right? WTS with VR now actually has a sizable commutator. So this norm can go, I don't know, order 1. So what this is saying is that in this system, the influence of a local operator spreads over a larger part of the system. And I talked about information because actually one way this becomes very important is precisely by thinking about if this were, for example, some qubit in which you encode some information, either by having it up or down or something like this, or it's a collection of qubits and you encode some secret message, then what happens is that here you can still measure that information. You can recover the secret by making a local measurement here. At this point, your information about this initial state is actually spread very non-locally, and you'd have to make a non-local, very complicated measurement to recover the information that was in that secret message. And so it can also be shown actually at the level of let's say, mathematical demonstrations that information spreading in a quantum system is intimately tied to the behavior of these commutators. But we wanted to go back to quantum chaos. So this is, by the way, already, I think, a very nice excursion that a tangent that I went on, which is that through these kind of measures in quantum systems, we actually start linking the idea of quantum chaotic behavior to the way that that information gets organized and spread across quantum systems. And that's a very deep. That's actually a very deep connection here. Okay, so I should also say that another thing that is visible here is that what happens is that Wt, which is e to the iht W0 e to the minus iht, basically spreads across the system, spreads over the system. Let me call it sigma. I could have just called this sigma, okay, over the system. And the operator becomes more and more delocalized, more and more complicated. And in fact, in a technical sense, as we shall see later, spreads over sigma and becomes more complex. And this is, I wanted to say this now because it is, as you appreciate, of course, one of the main links between chaos, complexity, and also later on how they manifest in gravity. So for example, one way of quantifying that this operator becomes more and more complex is literally by its size. How many of the, let's say, elementary operators that define my system, its Hamiltonian, do I need to describe the operator at a given time t? So complexity could, for example, mean size. But a more interesting question is, what precisely do we mean by complex? And that's something that I will try to address later. So for example, here we could have just said somewhat loosely that its size, in fact, this can be made precise, and it leads to, eventually leads to a notion that I'm particularly fond of, which is called Krylov complexity. Okay, but now let's go to the Lyapunov part. Okay, so OTOC, this all out of time autocorrelator, and a version of Lyapunov. Unless there are questions, of course. There is one.
I have a question regarding the cartoon. So when you say this WT spreads over sigma, what is sigma? Is it the phase space?
No, it's like here I really wanted it to be some sort of real space of the system. But better way of thinking about it would have been some sort of representation of the operator space of the system.
So WT is still a local operator?
WT is a local operator in the case of Einstein locality or something, was probably what you mean.
But this spread could also happen if the Hamiltonian is integrable, but it's just that when you discuss this.
Yes, that's right. So that's actually one of the, let's say that's one of the key things that we'll try to pursue, which is that the question is not whether or not the spread happens, but how does it happen? And so, for example, in a quantum system that is chaotic, it will happen exponentially fast. as we will say now.
And if it's a critical system?
A critical system in the sense of a conformal field theory?
In any phase transition?
Well, it could be also, I mean, depending on what assumptions you make, but I don't see any contradiction with the system being chaotic at criticality. In fact, there are systems like that I've worked on. But of course, it is true that, for example, if you think about very low-dimensional conformal theories, then you might be a little bit wary that there are too many conserved quantities. Like you have all the Virasoro algebra, and you have all of the KdV hierarchy of conserved charges. And in fact, I nowadays find these lower dimensional CFTs to be, again, the kind of system which, in some sense, really doesn't want to be chaotic, but I strongly believe, and so do many others, that there exist actually chaotic signatures in these theories. So they're a little bit also in between the two worlds. But there are all these conserved quantities that tell us that the system shouldn't be chaotic, yet there exist chaotic CFTs, or I strongly believe that there exist chaotic CFTs in low dimensions. In higher dimensions, of course, they exist. Yeah. Okay, so let me go on then. So the statement will be that you can read off something like a Lyapunov exponent because in Q local chaotic system, so Q local actually just means that you allow local systems, but you also allow systems which are somewhat non-local, but the non-locality is controlled in the sense that it only involves at most Q of the total, say, n degrees of freedom at a time. So in such a system, you have that this C of t and r has a behavior which is 1 over n, where n is the number of degrees of freedom, and it should be large, times e to the 2 lambda times t minus r over a velocity called the butterfly velocity. So if you neglect for a second the spatial dependence, the dependence in time, it's suppressed by this large parameter. You want something like large n semi-classical behavior. So that's one important thing to keep in mind. And secondly, I've already written here lambda. Maybe I should have called it lambda q for now. This is a quantum version of this Lyapunov exponent. And there is also something which I always have to reconcile myself with. I find it natural to write 2 lambda here. That simply goes back to the fact that you have a square here. There are other sources that I see every now and then which just call this lambda. Of course, the difference is just a factor 2, so that's not particularly interesting. But I find it natural to put 2 lambda here. And the second part is that what you have is you have some sort of ballistic spreading of a wavefront at a characteristic velocity that's called the butterfly velocity. So VB is called the butterfly velocity. Or, of course, in all of this business now, you should put quantum in front of everything. So it's really the quantum butterfly velocity. And lambda q is the quantum Lyapunov exponent. And when this resurfaced now, probably like 10 years ago, as I said, it was at first already present in works in the 60s, late 60s and 70s. But when it resurfaced, it was met with some excitement as yet another way of characterizing quantum chaos, but moreover, one that is sort of related to information theoretic ways of thinking about the system. And that remains is true is that this probably only makes sense really in large n systems because they can be semi-classical in 1 over n, or perhaps it makes also sense in some systems which are semi-classically in other ways, but it is at least something that is, if you want, the direct imprint of the classical chaos onto quantum systems. So in some senses, maybe less of an intrinsically quantum expression of the chaos than what we talked about before. And to this day, there isn't a relationship that is known between this kind of thing and at least not a causal relationship between this kind of behavior and that kind of behavior, or that kind of behavior and this kind of behavior. Would, of course, be nice to establish it, but so far it hasn't been. Okay, but what is very, very nice is that, also, by the way, this scrambling time t is equal to ts in such a system then necessarily goes like t is equal to ts, also sometimes called t star. Scrambling time will go like the log of the number of degrees of freedom of this system. And so it can be parametrically larger by log n than this dissipation time that I talked about before if n is a large number. That's another reason why n ought to be a large number here. But once you have this definition on your hand, there is one very nice thing that you can do, which is that you can essentially establish a bound of this quantum Lyapunov exponent, which is of the following form. Well, it's actually extremely simple. And I would maybe give you a taster of how one goes about establishing it. But there is something called the MSS bound, or Maldacena-Schenker-Stanford bound on this Lyapunov exponent. And it says that lambda is actually less than or equal to 2 pi times the temperature of the system. Remember, the temperature comes in because we looked at beta is equal to 1 over t density matrix when we calculated this. So this is saying that the Lyapunov exponent, the quantum Lyapunov exponent, cannot be arbitrarily large. And so that opens the door to saying things like, this system is more strongly chaotic than that system because this system is closer to saturating this MSS bound than the other system. And statements of that kind. Yes, you had a question.
Is this some sort of quantum field theoretic version of the Lieb-Robinson bound?
Well, Lieb-Robinson is more like this. And as far as I know, the butterfly velocity, so if you have velocities, you can define these cones. The butterfly cone, so if I have something like t here and x there, and this is 1 over the butterfly velocity, then the butterfly cone, and this is t is equal to t star, always has to be contained within, well, also I started at 0, but even the slope has to be strictly contained in the Lieb-Robinson cone, so V Lieb-Robinson, 1 over V Lieb-Robinson, because I'm plotting t against x. If you're a relativist, you might also put the speed of light somewhere here. But you asked about Lieb-Robinson. But the actual question you asked is whether there is a quantum field theoretic version of the Lieb-Robinson bound. And as far as I know, there isn't. But yeah, I'm not the world expert on that. But Lieb-Robinson is basically a way of establishing that even if you want, so this is for the members of the audience who might not be aware of what it is a way of bounding the spread of entanglement in a system. So it's also a very basic sort of hardwired notion of a quantum system, and it can be actually shown to be ballistically spreading and bounded, and so in some sense there is an emergent light cone in any quantum system, even one that is not relativistically invariant, which is related to the speed of the spread of entanglement. And nothing that I'm saying here violates any of those bounds. So even if the system saturates this chaos exponent and so on and so forth. Okay, so let's see. So maybe I won't go through the sketch of the proof because I want to get to complexity. But what I do want to say is that one thing I would like to remark is that so bound is actually for, I said that this is for the thermal state, okay, where I said rho is equal to e to the minus beta h. But in fact, the bound is not for this. It's actually this, in some sense, chopped into 4 bits. What do I mean by this? I mean that instead of writing trace e to the minus beta h times this sequence of operators, I actually write e to the minus beta over 4h, and then I have my wt e to the minus beta over 4h vt e to the minus beta over 4h vr, excuse me, v dagger r wt e to the minus beta over 4 vr. And so that's to say that I've chopped up the density matrix into 4 bits and I've actually inserted them between operators. You know, you can't use the trace relation to just reunite them all in front of it. So it is a different regularization of the thermal 4-point function. And it is necessary to regularize it like this in order to actually obtain this bound. This is just a remark. Okay, so now what we've said is that we have introduced classical notions of chaos and quantum notion of chaos, and we have kind of shown that at least the intrinsic ways that quantum chaotic systems manifest themselves seem at first sight very different from the way that classical systems behave chaotically. But now we have some notion which kind of has the possibility to bridge at least the two let's say the conceptual chasm between the two. And moreover, it's related to the spreading of quantum information, which makes it very attractive. So now what I want to do is I want to develop this idea a little bit, and I want to steer it in the direction of complexity. And complexity precisely will take here its departure point from appreciating that this spreading of information is actually linked to the way that the operator grows and becomes more and more complicated. And so in some everyday language way, it becomes more and more complex, but we'd like to actually make that a more mathematically precise, quantifiable notion. All right. So I want to talk a little bit about a particular notion of complexity, which will be Krylov complexity or K complexity. So, and the reason why I'm going to talk about this notion also, it takes in many ways its departure point by looking at this physics. So let's answer those questions that I put up earlier about complexity, like what does it actually really mean? So the most general notion, in some sense, quantum complexity, you can take a utilitarian view of this. It's essentially the number of, or the amount of resources needed to prepare a quantum state or a quantum system or an operator. Okay. And the state, or let's say operator. Okay. So the most basic notion here is also the most invoked example, which would be something like gate complexity. So the idea would be that you ask that you assign some complexity, let's say, to a state psi, C gate complexity, as roughly speaking the number of qubit gates you need to apply to reach some state psi, and we could also talk about unitaries or even Hermitian operators, but to reach some psi from a given reference. Let's say it's very easy to have access to the given reference state. For example, it might be a very easy, simple state or a natural state that your quantum system will naturally be found in or settle down. And then the question is, how many operations do you need to perform it? And operations here means qubit gates. I'll give a sketch of this in a second, in order to go to psi from a given reference state. And you can, in this sense, literally sort of put dollar signs on this, because let's say every gate costs you $1, then whether a system that has Hilbert space size d costs you order exponential of d dollars or order, let's say, some polynomial in d dollars, makes a big difference to your bank account when d is large. And so the interest is precisely in trying to delineate classes which may need exponentially many resources in this sense, or only polynomially many, or maybe even just order 1 many. So that's a very rough notion. And the idea is that you start with psi 0, and let's say this is a state that is prepared on a system that has many qubits. Then you want to end up in some state psi, which may be in some sense much more complicated. And then what you do is you evolve the system, and you put like 2 qubit gates, 1 qubit gates. You can put also like whatever controlled qubit gates. I mean, you can do with this thing. Well, not you can do what you want. You do what you need, and eventually, you end up with your state psi, and you count up how much did this cost you. This could be some Hadamard gate, this could be some X gate, this could be a controlled NOT gate, this could be a Hadamard gate, and so on. You count the number of gates that you need to ask Mr. Google to build in his quantum computer, or maybe eventually Mrs. Google, once the CEO changes, that she needs to build in her quantum computer, and you're done with it. And that's, of course, an extremely useful way of thinking about complexity, and it's one that's super intuitive. And I should say, by the way, Pavel and friends have recently written a very nice review on complexity in its generality. So this here was gate complexity, but there exist also other notions of complexity, such as Nielsen complexity. There also exist classical notions of complexity, like, for example, Kolmogorov complexity, because you could ask similar questions in an arithmetic in an algorithmic sense for classical computers, and so on and so forth. There exist many notions. But the one that I would like to talk about, because in my opinion it connects very nicely to these discussions, is this idea of K complexity. And so let's do that.
One question.
Yes.
What is the scaling? Like, what is this D?
Oh, this was the dimension of the Hilbert space. It was just this. We could also just say, really, the number of degrees of freedom, if you want, which I called n earlier. It's probably a better way of saying it, actually. Yeah, thank you. Other questions? I mean, this is really just meant to be a broad motivation. The Krylov complexity will, as you will see, have much closer relations to what we have discussed before. So maybe I will introduce it now, and then probably have time to develop it somewhat tomorrow. And then afterwards, we'll go into what all of this has to do with gravity. And in fact, there's some very recent, very nice connections precisely between Krylov complexity and gravitational observables. So the main idea in Krylov again is that it's like we were saying with the characterization of chaos in quantum systems. What we should look at is what we have at our disposal. We should look again at the simplest, well, not the simplest, really the only thing that we have, namely time evolution. Or if you're an operator, then time evolution for you is this, or I could have written down the Heisenberg equation of motion. Okay, so there is essentially notions of Krylov complexity associated to both. This here also sometimes is called spread complexity. It is in some sense Krylov complexity in the Schrödinger picture. And this thing here is, well, what was the original definition of Krylov complexity? And it could be Krylov complexity in the Heisenberg picture. Now, what do I mean now? So let's get a little bit of intuition. So if I take, for example, something quite close to this, I take some spin chain. I take some nearest neighbor interaction spin chain with n degrees of freedom as we had before, zi plus 1, plus I could add some bias in the xi direction and some field, let's say, in the z direction. Okay. Then, of course, if I look at Heisenberg evolution of some operator, for example, I could look at z1. So I could say that O is equal to z1. If I wanted to know what happens with this operator, I would say that I find that z1 of t, of course, is given by z1 plus it times the Hamiltonian with z1 minus t squared over 2 times the Hamiltonian with z1, and so on and so forth. I would just do the CBH expansion of time evolution. And so in a very naive kind of Taylor series way, I would say that the further I want to go in time, the more terms I need to keep in this Taylor expansion, and the more of these commutators I should keep. Okay, but of course also at every point in this discrete series of steps, you get something like we get monomials of the kind. Z1 becomes, well, you get something like y1. Then you also get things like y1 times zn. You get y1 times z2. You get something like y1 z2 zn, and so on and so forth. And so as the question earlier suggested, you get both some sort of spreading in real space, which was this butterfly velocity, and you also get a spreading in operator space, namely that the further you go in this expansion, the bigger this operator gets and grows and grows and grows. And so that means that we should think of this complexity both in terms of this kind of spreading along some cone, which is more the local structure, and also we should have thinking of it as evolving on a ladder of size where, roughly speaking, this is size 1, this is size 2, this is size 3, and so on and so forth. And as you go, so let's see, s is equal to 1, s is equal to 2, s is equal to 3, and so on. And you can think actually of the time evolution of the system as being like a wave function that may be localized somewhere along the size, for example, at s is mainly at s equals to 3 and s equal to 4, but that can move along the size distribution and spread out. And the bigger, in some sense, the expected value of the size is, the more complicated this operator is. And so you would define some basis which measures the size, and you would project z of t onto the size basis. You would say z of t, this operator, I project it onto the size basis, and I associate to this something like size complexity. Actually, this can be done and is still being done. It can be done very precisely and successfully, but in some sense, I will take already the next step, which is that I go to a very specific basis that is not the size basis, but that is something like the size basis. It's called the Krylov basis. And I measure the spread of this operator in this basis and associate this to complexity. And it's better than the size basis for reasons that I may or may not have time to explain, but that will certainly be, well, actually, we wrote a long review just now on Krylov complexity, so it's lots of details are in there, but they'll probably also be in the shorter lecture notes that we're producing for this. So let me just say, let me just end on this. So size complexity would be somehow the expectation value of size in naive basis, e.g. Pauli strings of length L or S, Pauli strings of length up to and including S, while K complexity is actually the same thing, and I will tomorrow define it in detail, but it's basically you take the basis that is, roughly speaking, size is equal to S. You don't use it. Instead, you use a basis that is, in some sense, how many commutators with the Hamiltonian, with the initial operator, did you need in order to describe the system at a given time? Or if you want, for a state, you just take your initial seed state, h psi, h squared psi, and so on and so forth, until h to the k psi, and so on to infinity. And you now construct from this a canonical basis that is like the size basis, only better in a way that I will make precise. And you then measure the expectation value where it is in the size basis as a function of time, and that gives you a very precise notion of complexity, which is intimately linked to this, and therefore also intimately linked to Lyapunov behavior. And if I have time, I will also tell you how it is related to spectral behavior. All right, I think I'll stop here for now. Thank you. Questions? Yeah.
So the definition of this complexity will depend on how you want the precision of your state.
I'm not sure I completely understand the question, but there's certainly one thing I want to say, so let me understand it in that way. Often it is said, and I have said it also many times, that in this kind of notion, for example, like gate complexity, there has to be a parameter which I didn't actually notice, didn't mention, which is something like epsilon, which means that you approximate your state or your unitary up to precision epsilon. And in some sense, epsilon is part of the definition of the complexity. One of the nice features of K complexity is that no such precision parameter is needed, so it's independent of such a parameter. But that may not have been your question. It was your question. Good. Yes?
So this number of commutators need not go to infinity, right?
No, of course not. Yeah. In fact, you can prove under certain assumptions that Krylov space terminates and is finite.
I mean, to me, okay, I mean, the number of commutators also kind of tell you the number of strings, right? Or maybe because in this particular example, it's the K.
No, it does, absolutely. Yes, I completely agree.
So, isn't this K complexity and size complexity a rephrasing?
No, well, Yes and no, but that's because there is one important bit that I didn't tell you yet. I mean, this basis, just like that, will not be orthogonal. And so what you do is you actually have to orthogonalize this basis. You have to Gram-Schmidt this basis, or in fact, there's a more efficient way of doing it, named after a physicist called Lanczos. And once you've done this, the state at order n will actually have contributions from all sizes. And what you can show, for example, is that size complexity, if you do it naively, saturates much earlier. It is much less rich in characterizing the complexity after a certain evolution time than Krylov complexity. And so in that sense, Krylov complexity is more powerful to follow the system to more interesting timescales, let's say. So it's not the same, but it's also like the way that I said it here very briefly. I understand why you might get the impression it's just the same, but it isn't.
Can I ask another question?
Yes, although I'm not the chairman, so the chair should decide.
I mean, to me at least at this point, even though you said you would comment on it later,
Yep.
how would you connect those two? Because there the Lyapunov experience.
What are you pointing to?
Like Lyapunov
Yeah.
experience had temperature, but here we're just considering state.
That's right, but that will be actually that will be in some sense an improvement, at least to some people's minds, of talking about Lyapunov this way and that way. The idea would be that that there is some thing called the Lanczos sequence Bn, which under certain assumptions in the thermodynamic limit has asymptotic linear scaling with n. N is actually the number of commutators, and then you Gram-Schmidt this thing. And the point is that alpha is actually a bound. Maybe I'm misremembering it, but now this gives you actually a bound on the Lyapunov exponent that is not dependent on temperature, and therefore, for example, that infinite temperature is strictly stronger than the MSS bound. But at any rate, the point is that the growth rate of the Lanczos sequence, which will also have its image in the behavior of K complexity, is something that is related to the Lyapunov physics. But that's not obvious from what I showed you here, of course.
Any other questions? Okay, if not, that was it for today. I'll see you all tomorrow at 9:30.
See ya.